So now we're ready to begin chapter 14, where we're going to talk about acids and bases. Again, as always, our book problems are going to be on slide 1. Now, on slide 2, we begin to talk about different types of acids and bases. So in 1880, a guy by the name of Arrhenius experimented a lot with electrolytes and basically found that acids are going to produce H plus and bases produce OH minus, specifically in aqueous solutions, or solutions that are made with water. Now, that meant that under this definition, an Arrhenius acid would have to be in an aqueous solution, okay, and an Arrhenius base would be limited only to OH bases, all right, or hydroxide bases. Later, a guy named Bronsted developed a Bronsted-Lowry model in which acids were defined as those species which donate H plus, and bases would be species that accept H plus. All right, now this allows NH3 or ammonia to act as the base, which it is, even though it doesn't produce any OH minus. Okay, so this is a broader model, okay, that allows us to consider that Bronsted-Lowry acids would donate H plus, and Bronsted-Lowry bases would be anything that accepts an H plus. Okay, and it isn't limited to aqueous solutions. Okay, so we have two different types of definitions for acids and bases. Right? Now, let's think about what happens when we add acids to water. Okay, and this is where we're going to be starting on slide 3. Okay, so if we add an acid to water, they are going to dissociate into ions. Okay, now, for example, we have HA, which is in an aqueous solution, plus water in equilibrium with an H3O plus, or a hydronium ion in solution, and an A minus ion in solution, where A is just some sort of acid molecule. Okay, now in this process, okay, each component is going to have a special name. So when we add an acid to a water, it's going to get a special name. All right, so if it loses a proton in this process, that makes it the acid. So if we looked at this reaction, we notice that HA on the other side has lost a proton and becomes A minus. That means that because this species was the one that lost a proton, this is going to be our acid. Okay? Now, once it has lost the proton, so we have our HA, once it has lost the proton and becomes the A minus, that makes this our conjugate base. Okay? So that is what's called a conjugate base. Now, it's called a base because now it can accept a proton once again. All right? Right? So it has a space that it could accept a proton. Now, and when I say proton, I just mean H plus. Okay? Now, if a molecule gains a proton in the process, then it's going to be our base. Now, notice that H2O became H3O plus. So it gained an H plus, or a proton. That means that since this molecule was what gained it, that becomes our base. Okay? And then once it has gained the proton, okay, once we've gained the proton, it becomes our conjugate acid. Okay, so now we're able to define each of the species in our reaction. Okay, so we have HA, which was our acid because it gave up the proton. We have our base, which was H2O because it accepted a proton. We have our conjugate acid, which after the base gained the proton, now it's going to act sort of like an acid because it can give up that extra proton. So it becomes a conjugate acid. And then we have a conjugate base of A minus because the acid lost that proton and became somewhat of a base because now it can accept that proton again. Okay? Now, lastly, when we're talking about acids and bases, right, if we're looking at our species here, a conjugate acid-base pair is going to be the pair of molecules that exchanges a proton. So, for example, let me use a different color. All right, if we were to find our acid-base pairs above, right, we know that HA and our A minus exchange a proton, right? They're going to swap it back and forth. Okay, so that is going to be our conjugate acid-base pair, right? And our H3O and our H3O plus and our H2O, those are going to be a conjugate acid-base pair. Okay, so we have two conjugate acid-base pairs in this process. All right? So those are going to be some useful terms as we go throughout all of the material in this chapter. All right, so I would work on memorizing those, as well as your definitions for Bronsted, Lowry, and Arrhenius acids and bases. Okay, now let's try to practice these definitions a little bit. I think that'll be helpful for you guys. Let's look at slide 5. Okay, and on slide 5, we're looking at conjugates. Right, where we were talking about our conjugate acid, conjugate base, that sort of thing. Okay, so we had the example on the slide of NH3 aqueous plus H2O liquid, all right, in equilibrium with NH4 plus aqueous plus OH minus aqueous. Okay, now in this particular reaction, okay, if it loses a proton in the process, it's an acid. Okay, now when I look at NH3 and I go to the other side, notice that it became an NH4 plus. So did this one lose a proton? Did it lose H plus? No. In fact, it gained one. We'll talk about that in a second. Notice that we have our H2O. Okay, H2O in this case became OH minus. Okay, that means that H2O lost a proton. So since it lost a proton, right, H2O lost a proton. Write that a little lower. H2O lost a proton. So that means that H2O is our acid. Okay, so this is our acid. Okay, now since it lost the proton, once it lost the proton, it became OH minus, which means that OH minus is our conjugate base. Okay. Now we can look at our NH3. We saw that NH3 gained a proton. Right? It gained an H plus. So if it gained an H plus, it makes it a base. So we know that our NH3 is a base, okay? And since NH3 gained an H plus and became a base, that means it is a Bronsted-Lowry type base, right? Now, also, once it gained the proton, that meant that NH4 plus is now our conjugate acid, okay? Because it has an extra proton. So this is our conjugate acid. All right, so that should be pretty straightforward. Right now, what are our conjugate acid-base pairs? Well, we have NH3 and NH4 plus, right? That would be one conjugate acid-base pair. Okay, we also have H2O, and H2O became OH minus in this case, so that meant that this was another acid-base pair. Okay? So let's do another example. Our next example is going to be on slide 6. All right, so for this reaction, we have H2SO4 plus H2O in equilibrium with H2SO4 minus and H3O plus. Okay, so which one gained a proton? Or actually, let's do it this way. H2SO4 becomes what? It becomes, and this should be, I'm sorry, this should be HSO4 minus. Okay, so our H2SO4 became the HSO4 minus. So that meant that this one lost a proton. since it lost a proton, right, it's donating a proton, that means that this is our acid, okay? And if that's our acid, that makes this our conjugate base, all right? Now, look at our H2O. H2O became H3O plus. So that means that our H2O accepted a proton. It gained a proton. So that meant that this is our base, okay? And that this would be our conjugate acid. Okay, so pretty straightforward. Let's do another one. We have HCO3 minus plus H2O in equilibrium with H2CO3 plus OH minus. So now we have HCO3 minus, and what does it become? Well, HCO3 minus, notice that over here it became H2CO3. So did this gain or lose a proton? It gained a proton. That means that this is our base. And once it gains the proton, it becomes a conjugate acid. Okay? Over here we have H2O, and it becomes OH minus. Okay? So what happened to our H2O? Did it gain or lose a proton? Well, it lost a proton, so it could become OH minus. That means that this is our acid because it donated the proton, and this is our conjugate base. All right? Now, the next thing that I want to talk to you about on slide 7 is the idea of acid strength. Right? A lot of times we want to know how strong an acid is, okay, or a base for that matter. Okay? So, the idea of acid-base strength is that the strength of an acid is determined by the equilibrium position of its dissociation reaction. Okay? And that's a whole bunch of words that basically means it's the reaction when we have a species giving up or dissociating into the H plus and the A minus. So for instance, right, if we had some acid HA and we added it to H2O, right, this HA is going to be giving up, it's going to be dissociating into its ions, right? So this would become H3O plus and A minus, okay? Another way to think about it, right, is that H3O plus is basically like an H2O and an H plus. So if we got rid of our spectator ions, the dissociation reaction would look something like HA becoming H plus and A minus. Okay, because the H2O is just a spectator, it's not participating in the reaction. Okay? So if we look at that, right, we know that we now have dissociated into our ions. So it's determined by our equilibrium position. So we're looking for our Ka and the concentrations associated with this HA splitting up. Okay? Now, for a strong acid, the equilibrium lies far to the right. Right? In other words, for a strong acid, since it lies far to the right, it favors being dissociated. So a strong acid completely dissociates. Into ions. All right? Similarly, a weak acid, okay, is only going to partially dissociate into ions. All right? Now, if we're looking at that equilibrium, right, and our HA completely dissociates when we put it into water, that means that rather than having an equilibrium, our HA just has a single forward dissociation arrow to H plus right? H plus and our A minus. So there's no equilibrium, all right? We know that for strong acids, it's going to completely split up and it's not going to go back to our HA unless we removed all the water, okay? For a weak acid, however, right, it only partially dissociates. That means that we have some that's completely dissociating, or we have some that's dissociating, right? We have our H plus and our A minus, but we also have some of that ends up reforming to give us our HA, okay? So strong acids completely dissociate, and weak acids form an equilibrium. All right, so now you can begin to see why we discussed our equilibrium chapter before we started on acids and bases. All right. Another couple of comments that I wanted to mention is that strong acids have a large Kc or what's called a Ka because they're acids. Okay. I think usually they use a little a. Right? So we have a large Kc, which is usually for acids called a Ka. The Ka is a dissociation constant for an acid. Okay? So in other words, right, like I was just saying, if we had HCl, HCl is a strong acid. That means that when we draw our equilibrium, right, we know that we're going to favor our products. So we have H plus and Cl minus, and we'll have a little bit going backward, right? Again, it's favoring the dissociation, right? Now, weak acids, again, just to reaffirm that point, have small dissociation constants, all right? And they're going to favor the reactants. Okay, so we would have HC2H3O2, right? That's acetic acid. You guys should remember your polyatomic ions. And that's going to dissociate into H plus and our acetate ion, which is C2H3O2 minus. All right. Now, we're going to have a little bit that dissociates, but we're going to have a lot that wants to stay as our acetic acid molecule. Okay. So it's not going to completely dissociate. Now, that idea is shown in pictures on slide 8, right? Where it's completely dissociated into ions for our H plus and Cl for hydrochloric acid, right? It's showing you hydrochloric acid in that first picture. And in the second picture, it's showing you acetic acid, okay? And basically what that means is that strong acids, they usually form good electrolytes. Because they form ions. And your weak electrolytes, or your weak acids, are usually weak electrolytes. Okay? We'll talk more about that a little bit later. Now, one thing that I want you guys to do on slide 9, all right? On slide 9, you'll see a table of common acids and bases, or sorry, some common acids. All right? Now, I want you to memorize that table. Okay? You're going to need to know both your strong acids and your weak acids. So I'm expecting you to know that HCl is hydrochloric acid. And I'm going to want you to know that hydrochloric acid is a strong acid. Okay? I want you to know the formula, like the chemical formula. I want you to know the name, and I want you to know whether or not it is a weak or a strong acid. Okay? Now, how much time do we have? Oh, we've got a little bit of time. Good, good, good. Now, as I mentioned, your strong acids, they're going to dissociate completely. But the weak acids, right, they end up forming an equilibrium. Okay? So, since we're talking about equilibrium, let's say that we look at slide 10. And in slide 10, we're going to use some of those ideas that we talked about last chapter, okay, and discuss the equilibrium expressions for acids and bases. Okay? Now, as I mentioned, we have a Ka. Our Ka is our acid dissociation constant. Okay? It is specific to an acid, like hydrochloric acid, or since we're wanting to talk about maybe weak acids when we deal with Kas, it would be more common to use it for acetic acid, for example. So a Ka for acetic acid at a specific temperature would usually be given to you, or you'd have to determine it, okay? But it is going to be a constant, right? So let's say that we have some general acid HA in equilibrium forming H plus and A minus, okay? Where A minus is just what's left over from our HA molecule, okay? In the case of the HCl, the A would be the Cl, okay? In the case of our acetic acid, it would be our acetate ion, okay? Or our acetate part of the molecule, okay? So if we have this dissociation, right, then our Ka, right, since it's an equilibrium constant, specifically for acid dissociation, this is our dissociation, right? We have our ions on the right, it's dissociated. That means that when we build this, we're going to have products. So our concentration of H plus to the first, concentration of A minus to the first, all over our reactants. So we have our concentration of HA to the first. And since it is the dissociation, it will be at equilibrium. Okay? So that would be how you define your acid dissociation constant. Okay? Now, when we write our reaction, right, sometimes we write it as HA plus H2O in equilibrium with H3O plus and A minus, right? Since water, we talked about this, since water doesn't really participate in the reaction, right, we're going to ignore it and exclude it from our Ka. So even though it's written like this, right, Ka is not going to have water in it. Instead, if we wrote it this way, it would look like products over reactants. So we would have H3O plus to the first, A minus to the first, again, products over reactants, and then our reactant is HA to the first, all again at equilibrium. Okay, you could write it either way. Just know that the H2O is not going to be part of your Ka expression. Okay? As a note, always exclude water in your Ka. All right? Now, one last thing that I wanted to mention is that the stronger the acid, the bigger the Ka. Right? And that should sort of make sense. The more it dissociates, the bigger those numbers get, the bigger the Ka. So, to write that down, we have the stronger the acid, the larger the Ka. Okay? So, strong acids have a Ka greater than 1, okay? Because they favor the products, right? And weak acids have a Ka less than 1 and favor the reactants. All right, so that covers our introduction to acids and bases. All right, and we'll continue in our next video.